Okay, good. Yeah, thank you very much for the chair. It is my pleasure to be invited to give a talk. I think hopefully that it could be even better that if I joined in the meeting in person, but during the semester, long international trip is always kind of a bit difficult. So sorry that I just kind of present over the Zoom, but hopefully that we can still kind of interact quite heavily. So I know that this symposium is interesting because it's the combining various ideas, especially this fractionalized charge excitations and strong correlations, and hopefully that the talk that I'm presenting today make the kind of deep connection with the main topic of this conference. So I'm going to talk about combining the fractional quantum Hall effect and the superconductivity. And obviously, this talk is not possible without the wide range of the collaboration. So the main part of the talk, the last part, especially important part, is basically carried by these two former postdocs on the Gore and the Yuval Ronen. On the move back to Delft, and the Yuval is now in the Weizmann, and with the students and the former member Gil Hori now as a postdoc. In collaboration with SKKU, that led by Young-Hee Lee. And then we have also the very strong theory support by the Ashwin Viswanath group, led by the Hassan Shaparian. And some part of experiment is in collaboration with the Amir Kobi group and Bob Westervelt group at Harvard. Okay. So let's step back and kind of give the little bit broad perspective first. Quantum mechanically, when we have the two indistinguishable particle, because of this exchange symmetry, anything that beyond the three dimension, there is additional this symmetry that imposed by the exchanges, and that lead into this any indistinguishable quantum particle in higher dimension in the kind of two kind. Either it could be boson or the fermion. Depends on that when you exchange this particle, whether you get this negative sign or not in front of your wave function. That will just kind of determine that whether one characteristic is boson versus fermion, and that those are one of the important fundamental quantity that determine that quantum statistics. Now things becomes different when we move this indistinguishable particle into two dimension. In the two dimension, basically because of this dimensional confinement, when you just do this the exchange of the particle, that lead into the equivalent of this the winding of particle, one particle to the other one. And in 2D, basically its winding number is a well-protected topological index. Therefore, that this exchange statistics may provide of the more of the possibility, including the boson and fermion. In fact, the phase factor in front of this wave function can be that the pi plus minus pi divided by any integer numbers. So therefore, the possibility that going beyond of the boson and fermions are possible in the two dimensions. However, even more exciting part, and often that this is what you call the anionic the quasi-particle. Even further, that if you just allow the degenerate ground state of the particle, there's a possibility even after this the exchanges, particle can map into the one type of the quantum ground state in the 2D to another one. So this so-called exchange operation may lead into the even just a non-Abelian characteristic, and often that this anionic quasi-particle in the 2D can be typically the Abelian quasi-particle that determined by this phase factor, or that ground state is non-degenerate. It can lead into the so-called non-Abelian anionic quasi-particles. And in particular, this non-Abelian anionic quasi-particle is kind of very exciting in a sense that because of this the non-Abelianity, that the braiding of these quasi-particles of the pairs are possible, and often already it led into the multiple quasi-particle braiding can lead into the new quantum state, where the quantum state information is encoded in this topological natures of the braiding, the operation. And obviously, this type of this braiding, the topologies in the 2D, the non-anionic quasi-particle, has been proposed to be used as the topologically protected qubit the platform for some times. So in past probably 10 or 15 years or so, even 20 years, so per se, that there has been some of races that to realize that this non-Abelian, the anyonic quasi-particles, and then demonstrating their physical existence as well as the braiding operation of between them becomes quite important issues. And there has been some platform, concrete platform has been suggested. For example, that 5-half fractional quantum state, it is believed to be that it is a more real state. It's quasi-particle. Should be it's presumed to be non-Abelian type of the quasi-particle, and there has been the wide range of the theory and experimental efforts to realize those kind of prove that those kind of nature of this the non-Abelian nature of this quasi-particle has been on the races. The other platform is the combining the superconductivity with the various different topological platform. It could be topological insulator, or 1D ferromagnetic wires, or the atomic chains, combining of with the superconductivity or proximatized of this topological system, often can lead into the Ising type of the non-Abelian the quasi-particle called Majorana fermions. And there has been some of this experimental, the theoretical platform, as well as experimental, the demonstration has been attempted in past probably decades or so. All of these things basically is the kind of tied to the possibility bringing to the topologically protected quantum the computing onto some of the solid state platform, and that's kind of one of the major motivation behind this type of the race. What I'm going to discuss today is a yet different material platform that could be a little bit related with the previous kind of slide, but somewhat different the operation. And the material platform is realized into this 2D van der Waals system, and particular that in combination of the graphene with this insulating platform or the boron nitride, and maybe combined with some of the superconductivity can be the hybridized with those kind of system. One thing nice about the 2D material is that it has been demonstrated one can make the heterostructures out of this van der Waals stacking with various different type of the materials. And this technique, especially combine the graphene with the boron nitride, it has been demonstrated that one can create this extremely high quality two-dimensional electron system that can be created by sandwiching the graphene in between the boron nitride and making the contact through this side, the extremely high quality electron gas whose mobility is basically limited by the size of the sample, meaning the mean free path of the electron can reach easily tens of micron or even hundreds of micron. That depends on the size of sample, which provide us kind of extremely interesting the platform to realize a quantum device based on this graphene encapsulated boron nitride. Furthermore, when you apply the magnetic field onto the graphene system, especially single layer, even or especially in the bilayer graphene, it turns out with a decent magnetic field, something like a 10 Tesla or 15 Tesla, about the magnetic field that one can apply inside of the lab, that one demonstrated that indeed the even denominator, the fractional quantum state appears, and potentially the realization of this non-Abelian anyonic quasi-particle in such a state is kind of possible in this graphene platform, provide us that new design of the platform that one can work on to the quantum devices. Using the graphene, try to make this the various the quantum Hall device in the Majorana scale has been demonstrated quite widely. I'm going to show you that here's some of their recent efforts. For example, here that we encapsulate the graphene in between the boron nitride. Again, they encapsulate with the graphite, the top and bottom, and then one can make this pattern onto the graphite gates. This type of the devices, by controlling the top gate, one can guide this quantum edge state by just the designing of this top gate structures. In this particular part that we can create this particular path of this quantum edge state through this the defined edges, allows us to create this the quantum or interferometry, and in this way that we can just measure interference pattern throughout this Fabry-Perot interferometer built on this the quantum energy states. This type of the experiment is a very important tool which has been used in gallium arsenide, try to understand the quantum statistics of this quasi-particle in the system, extending this type of the quantum state in the fractional quantum state, which has been already demonstrated. There's a possibility just using this type of the quantum Hall interferometer, try to understand this the braiding statistics of the some of the exotic fractional quantum state. What I'm going to discuss today is not this topic, but related, but somewhat more exotic states I'm going to kind of present. The exotic state that I'm going to present is basically combining the superconductivity with a fractional quantum state. Now, both the superconductor and fractional quantum states are one of the two of the good examples that strongly correlate system we can bump into in the condensed matter system. But hybridizing these two has not been so popular. Part of the reason is there is a technical difficulty to realize those two phenomena in one system, simply because superconductivity hate to have this the magnetic field which tend to break the Cooper pair, while the fractional quantum Hall states require the strong magnetic field to realize this Landau quantizations and the induced strong correlation within the Landau level. And therefore, that's realizing the two systems at once, we need a little bit more careful engineering of the material platform. Nevertheless, theorists already just proposed that what do we expect once you're combining these two systems? I'm showing you here that's a paper that done by the Shucheng Zhang and his colleague in 2010. In this paper, the Zhang group argues that if you proximatize a quantum Hall system with a superconductor, note by the way, they present in this paper is a quantum anomalous Hall system rather than quantum Hall system, or make the comments in a moment, and that they demonstrated that if you just proximatize the quantum anomalous Hall system with a superconductor, once you thread this defect through these vortices, this vortices contains the Majorana zero mode and the vortex core, where the other the conjugated Majorana is edge states, and this which actually will allows to braiding this Majorana throughout these vortex operations in this type of combined system. The reason that Shucheng's group use a quantum anomalous Hall system is, of course, if you just use a quantum Hall system, similar things work it out, except that superconductivity may destroy by the strong magnetic field. They need the quantum Hall system, but nevertheless, the physics can be mapped from the quantum anomalous Hall to the quantum Hall states without a problem. Indeed, just kind of taking this even further, within a year or two, there are further more of the theoretical proposals expanding this idea further, that what if that you just proximatize a fractional quantum Hall state with this the superconductor, the extending the Shucheng's original idea. The couple of the papers that including Stengel and then some other competing groups of the 3 or 4 group about the same time, just demonstrated that indeed, if you expand this idea with the proximatizing the fractional quantum Hall state, at the vortex core, that you just nucleate this non-Abelian anyons, more generalized version of this Majorana, which is Ising non-Abelian anyon. In this particular case, in fractional quantum Hall states, you get this the generalized non-Abelian anyon called the parafermions, whose the algebra is much more complicated in a sense that which allows us more of this degenerate ground state in the system. In fact, just kind of bringing this the parafermionic state is actually even more exciting than compared with the Majorana based on the superconducting, simply because availability of this multiple the copies of the ground state allows us that this topological superconducting operations based on this parafermion can be much more close to universal quantum computing, simply using this multiple the ground state availability of the multiple ground state of the system. So there has been a lot of this incentive and experimental motivation, indeed, just kind of combining the fractional quantum Hall state with the superconductor. Experimental the attempt also has been realized by the few groups. For example, And this very similar work done by the Leonid Rockinson's group at Purdue, that the Rockinson's group that laid down the niobium, which actually HEC2 is something like the 5 or 6 Tesla, such that if you just kind of make the good contact with the gallium arsenide, with this niobium, at least that you can make this coexistence of the fractional quantum state, while the niobium still contains this the type 2 superconductivity in the system. And they see that somewhat unusual behavioral quantum states in their sample. And this experiment has been kind of difficult to reproduce by the many other groups. Part of the reason is making good contact, especially the good transparent contact between the superconductor and the semiconductor, such as gallium arsenide, is rather difficult because of the presence of the Schottky barrier, right? The graphene, in some sense, provides us the good platform, partly because the graphene does not have the gap, the band gap, such that if you just make the contact on the graphene, often that you can overcome that the presence of the Schottky barrier by just can properly choosing the good semiconductor, the good superconducting materials. And there's been some series of the work done by the Finkelstein groups at the Duke University. For example, here's one example. They made a contact of the graphene with the molybdenum rhenium and demonstrated indeed that they can make the Josephson junctions out of the molybdenum rhenium while it is in the superconducting state. Josephson junction through this quantum state has been demonstrated. That as shown, as the data is shown here. And this is a nice way that you can indeed kind of push that existence of the superconductor together with the quantum Hall, and potentially this supercurrent may be carried by the group of pairs. However, the problem of this type of experiment is, as you shown here in this example, that indeed that you see that supercurrent flow that within the plateau of the certain the quantum Hall states they demonstrate in this two-terminal device. But whenever there's the supercurrent is flowing, that by definition that you get the zero resistance, while that the having the quantum plateau in this two-terminal Josephson device, one expects to see the finite the conductance. Therefore, the true coexistence of the superconductivity and the quantum system is a really difficult to find out this type of experiments. But is there a way that indeed that one can then demonstrate it unambiguously the coexistence of the superconductivity and quantum energy state? More precisely, can I proximatize the quantum energy state with the superconductor? One way we can envision is using Andreev reflections rather than the Josephson effects. So in Andreev reflections, we know that when electron that impinging from the normal matter to the superconductor, electron turn into this Cooper pair by just kind of grabbing that electrons nearby to form the Cooper pair, and the whole is retro-reflected from the interface between the superconductor and the normal metal, right? And for this one, especially when you have this highly transparent junctions, you get the even enhancement of the conductance when this Andreev process is happening, and which actually one can use as evidence of this Andreev reflections. Now, if you just expand this idea to the quantum system, then one can just design the following experiments to tell that whether the quantum energy state got the proximatized. Imagine that I have this whole bar, and then I just have this four contact. I just bias from one of the contact and drain through the other contact, and just I measure the voltage in the one side versus the other side in the presence of the current is carried by the quantum energy state. Now, the quantum state means that all the current is carried by the edge state, and then edge state is a chiral, which means that this contact, which actually received all the current from the injected the current with the chemical potential of the V, will just read off the voltage V, while that the other side of contact, where that any current or any electron starting from this the ground state, the grounded junctions, which is carried the zero chemical potentials, they're running down and just equilibrate this junction with the zero the chemical potentials, which actually provide us that the total the whole voltage buildup the V, which actually translated RXY, the whole resistance is just quantized numbers with the nu is the number of the edge state carried by this edge state. Now imagine this quantum state that we just replace the downstream, the conductor as a superconductor and yet grounded, right? What is happening is then electron that just kind of coming from this upper edge state that they hit this the superconductor, but then it should go through the Andreev process, which means that that Cooper pair is created, but hole is retro reflected back. But hole as a missing electron will just kind of create just follow through this edge state and then create another the Andreev process, and then this time the hole like the Cooper pair is formed and the electron is bouncing off. And this process will go over and multiple times through this peripheral of this superconductor. And as long as this superconducting contact is much longer than the magnetic length scale, eventually in the downstream, you will have about the equal mixture of the electron hole in the system, such that downstream that you still get the 0 volt. So, and the quantum hole resistance you are measuring is still quantized in the same way. So what you see here is simply just quantum hole measurement. If you just do that, although the Andreev process is happening, you may not be able to detect by just measuring the voltage and current into this type of the system. However, this argument will be changed if you make this superconducting electrodes very thin. And what could happen is just kind of the upstream electron that coming down to this superconductor hit this contact, and then instead of the grab the electron from the same side, electron can be grabbed from the opposite side, and the hole can be created, and this hole can be traveled downstream. But this hole, which actually carries the same voltages, but except a negative sign because of this energy conservation, hole will carry the negative sign. Therefore, you expect to see that in this presence of the cross-Andreev reflections, that you should get the negative voltages downstream read, and then basically seeing that the negative signal is a good indication indeed that cross-Andreev reflection is happening, and indications of this proximatizing the quantum edge state. This experiment was kind of beautifully demonstrated by the Giro Reed, and when he was working with me a few years ago, and here the graphene that in contact with an iodine nitride, that once the graphene is getting into the integer quantum states, and then if you just measure the downstream the voltages in after this superconducting electrode, which is grounded, you see that in each of the quantum states, it shows that the well-developed negative voltages, which can be interpreted as indeed we get this the cross-Andreev reflected hole on the downstream as a presence of this the proximatization of the quantum edge state. The one way that you can view this cross-Andreev reflection, however, is the following way. So to make this type of the superconducting electrode, we make the trenches out of this the graphene, and then when we apply the magnetic field and quantum edge state build up, the quantum edge state kind of coming down here and make this type of the edge state of the flow. But now the trench is filled with a superconductor, meaning that across this two edge state counterpropagating across the superconductor can be proximatized by the superconductivity. And that's basically cross-Andreev process I just described, right? But then if you just look at this process, this is precisely that semiconductor nanowires that they proximatize the superconductor. And in the end of the result that we expect to see that that one of this localized Majorana zero mode actually appears at the end of the 1D superconducting wires, and the other Majorana might be just delocalized around these edge states. And indeed, this might be just a kind of one of the cases one can create this type of the Majorana type of the edge state in the system. Now, is this really that happening that to do with something cross-Andreev reflections? One way that you can demonstrate indeed this cross-Andreev reflection is the really important ingredient is make the superconducting electrode is not thin, but thicker and thicker. And indeed, experimental evidence, we just start to see that is this negative downstream resistance normalized by the current, which we can call this the downstream resistance or Andreev resistance, which actually negative numbers, quickly just kind of decreases. It's at the size as you just make this kind of the electrode thicker and thicker, indicating that indeed the thinness of this superconducting contact approaching this the superconducting coherence length is a really important ingredient to realize this system. Now, I'm going to demonstrate that using this cross-Andreev reflection technique enhance the device quality such that now we just push the quantum state into the fractional quantum state. I'm going to argue that we can actually observe this cross-Andreev reflections into the fractional quantum states, and that is one of the indications. Indeed, now we can proximatize of the fractional quantum edges in a similar way. For that, we have to increase our device quality even further. So I briefly mentioned that when you encapsulate the graphene in between the boron nitride and encapsulate again with the graphite, one can get even higher quality of the device. Here is a device that we use in this experiment. So now again, graphene is encapsulated boron nitride and graphite top and bottom gate is kind of installed. And then we have this 1D niobium nitride wires installed such that you can keep the superconductivity even at the higher magnetic field. And particularly in this the very narrow superconductor, the much thinner than 100 nanometer superconducting electrode is important. But also we just make this top contact nearby such that we can separately control that density nearby this superconducting regions. Using this experiment, basically we just follow through a very similar experiment I just discussed moments ago. So we will just kind of measure downstream the resistance, downstream the voltages, and the normalized current, which actually give us that cross-Andreev resistance, which should be just negative numbers bounded by the half of the RXY times -1. So that's basically experimental observations. And one thing you can also realize is normalizing the cross-Andreev resistance with the RXY, that you can get also how much probability that when electron is impinging onto this or any quasi-particle, charged quasi-particle is impinging on the superconductor, how many of them can be cross-Andreev reflections can be obtained by just making the ratio between cross-Andreev reflections with RXY value. Right, I'm going to show you that how this cross-Andreev the resistance, car resistance should look like as a function of gate voltage at a small magnetic field. And small magnetic field that you are not yet completely developed this fractional quantum Hall, but high quality device already for Tesla, you can develop all this broken symmetry, the quantum Hall states, that including now that well-developed negative cars appears. So the car value becomes, our car is increasing as the filling fraction is decreasing. Interesting enough that when you normalize the RXY value, that we get more like the constant, regardless of all these integer values of the system. Indeed, it's a constant integer, the probability of the curve for the integer edges, strongly indicating that the probability of the curve for the channel is the same. And this type of the behavior can be explained that indeed each of the quantum edge state make the pair between them. And then there's a topologically protected gap opens up if you consider strong spin-off coupling of the superconductor, and that will provide us this robustness of the car probability, regardless of the adding up this quantum edge state. So that's actually kind of quite nice, at least kind of prove the idea that presented in original the experiments now much more robust way and quantitative way, the integer. What if we just can push this now into the fractional quantum state? So the first thing we notice that is when this fractional quantum state appears, and for example, 1/3 and 2/3 and 5/3 in these experiments, that indeed our car is very strongly developed in the system. And the first thing we notice that is our car is even more stronger, even stronger than even integer cross-Andreev reflections. For example, they compare the 1 and 2. That if I just look at the 1/3 and the 5/3, basically the 1/3 and the 4/3, the car probability almost reaching the 10%, while that certain fractions, the car probability is about similar. to the integer. So there's kind of different type of this Carr process appears for the fractions, but the most exciting part is a certain diffractional quantum state, cross-Andreev reflection, cross-Andreev, the process is even more stronger. Not only that, temperature dependence of this process can be quite kind of different once you compare with a certain fractional quantum state with the integer quantum state. And this is indicating that at least we can explore different type of this the underlying mechanism that appears in this the fractional quantum state of the cross-Andreev reflection. It's kind of following way. There's two different scenarios possible that when I send this the fractional quantum edges into the superconductor. For now, let's think about the 1/3 state for the simplicity. The 1/3 state that we know that edge state carries this the quasi-particle charges about the 1/3, precisely 1/3, right? So that this quasi-particle in this the 1/3 the quantum edge state carries the 1/3 of the charges. When it impinging onto niobium diselenide and try to process the cross-Andreev reflections by creating the Cooper pair, there's a kind of one possibility is to make the Cooper pair that I have to collect all these 1/3 charges to form this the full charges, and then I can just make this the hole, grab the hole from the other side in the very similar way of the collection of all 1/3 charges, and then I can form the Cooper pairs and create this the Carr process, and then this the hole will break it into the 1/3 charge one by one, and then again that upstream the downstream charges carried by the 1/3 or negative 1/3 of charges. This could be the first scenario. Now this scenario requires that you have to collect all these fractional charges to make the full charges around. The other possibilities is rather than making this full charges to make the cross-Andreev process, we can just directly grab the anionic quasi-particle in the both sides and just make this Andreev process, and then you can just make this a charge to E star, where the E star is 1/3 of the Andreev pair process. In fact, this process, this microscopic process, is equivalent to create this the parafermionic states at the end of this superconducting wires. Is there a way that we can distinguish these two processes? As you can imagine that the collecting this the quasi-particle to form the full particle, that is not the ground state kind of the process, which means that if we follow through this type of the pairing of the states, as you go to the kind of lower temperature, you need excited to form this type of the collection of quasi-particle. Therefore, temperature dependence tells us, will tell us that this process is suppressed as you go to the lower temperature, while this the process, which is kind of basically rely on the single quasi-particle states, that can be even stronger as you go to the lower temperature. Indeed, if we just compare with our Carr process, a fractional Carr process as a function of temperature, we start to see that this is strong Carr that in the fractions, unlike the integer where it is saturated, it becomes stronger and stronger as you go to the lower temperature. Seemingly, that's that support that idea of this the pairing of the charge 2e type of the Andreev pairs in this type of the system. So that's actually again give us the sense that the fractional quantum state, the Carr process is kind of rather different. And now I just kind of told you that there are certain fraction is very strong. But certain fraction, the Carr process is following the integers. Why this make the kind of such a difference? In fact, this can be actually viewed by just looking at the detail of this Carr process. I told you in the beginning that when we make these devices, we make this top gate as well as the bottom gate with a different shape, such that we can gate to these regions near the superconductor in the different density. So right near this superconductor, versus away from the superconductor, by just action of the top and bottom gate voltages, we can just kind of fill up the different the density in the system. Now, using this one, basically this diagram is drawing this how the Carr process is changing. The bluish color is where that we see the cross-Andreev refraction is happening, right? Just note that this integer, state, nu equal 1 state, right? So we see that the chi is happening here, but once you just change the filling fraction around the superconductor, this chi process is basically just keep staying there, even if I just kind of filling up the near the superconductor more than nu equal 1 states. And this is what we call the accumulate regimes, right? While that, if we just move in different directions and then deplete that near the superconductor regimes, basically the chi processes disappear. And this can be understood simply just kind of looking at how the edge state configuration is changing. Nu equal 1, even at the accumulation ranges, this edge state will be delivered that kind of deeply into superconductor. So even with accumulation, we do not expect that the chi process chi process will continue, and this is why that we even in the accumulation region that we got a very robust chi process happening, right? Now note that if we just look through the 1/3 of the quantum state, that's not the case, right? So 1/3 state, we see that this the fractional quantum or the chi process is happening, but if you go to the pinching region, of course the chi processes disappear. But interestingly enough, that unlike the nu equal 1, if you go to the accumulation region, yet we also kind of remove this chi process, right? So 1/3 and 2/5 state, that strong this chi process happening for the fractional quantum or somehow, unlike the integer, we have the pinching and accumulations, both cases where we just kind of destroy this chi process. And that's because the edge state configuration of this fractional quantum or edges compared with the integer edges, that is different, especially in the accumulated regimes. Basically, the chi process is delivered by the integer, and then there's equilibration going on, which actually can destroy this chi process completely. However, some of the fractions, such as say 2/3 and the 5/3 type of the states, that where that this is a particle Hall conjugation, the edge state configuration is more like the integer like the state, even for the accumulation ranges. So in those kind of cases, if you go to the accumulation the region, you don't see the chi process. Basically, there the chi process is seamlessly delivered through this conjugate these integer quantum edges. All these things basically tells us now we can have this even explanations how that why the certain chi process is strong, why the other one is just as only as strong as only like the integers. Okay. So at least I just can hope that convince you that indeed we can approximatize the fractional quantum or edges, and likely that we start to create some of the unusual states at toward the end of the superconductor. What is the next step? Of course, the next step that we want to demonstrate is if it is a really non-Abelian anyonic form at the end of this superconducting wire, can you actually create some of the interactions even before just kind of braiding? So that we already start to make the Josephson junctions now using this twin finger, where the supercurrent is basically carried through the zero mode state, and see whether we can see the true coexistence of the superconductivity and the quantum states. Indeed, in this type of experiment, we already started to demonstrate it. The superconducting, the Josephson critical current is basically showing some of the step like the quantization behavior. Indeed, the kind of coexistence of superconductivity and quantum state can be demonstrated. Furthermore, that indeed if it is zero mode, that we can actually tunnel into this zero mode with the quasi-particle. And we are just trying to now create those kind of tunneling contact to just kind of aiming to toward the end of the superconducting contact, to demonstrating that this type of quasi-particle tunneling is possible. So I think these are kind of some of this ongoing experiment demonstrating that eventually whether one can reliably create those kind of the non-Abelian, the anyonic, the quasi-particle based on that combination with the superconductor and this fractional quantum edge states. With that, let me just kind of summarize my talk that I just kind of show you that using the cross-Andreev fractions, we demonstrated we can have this approximatized fractional quantum edge state with the superconductor. And then very strong chi process has been seen that indeed some of this the fractional quantum states. Thank you very much for your attention.
Thank you very much, Professor Philip Kim. Now the talk is open for questions. Please. Okay, let me start. So you mentioned that there is some independent of negative resistance as a function of filling.
Yeah.
So I didn't catch the reason, although you explained. Will you re-explain that part again?
Yes, I went through it. That's right.
Yeah.
So if you just look at this this graph, so we already normalized the car with RxY, and this will give us that the probability of the car per any impinging particle into the impinging particle in the system. So experimentally, we see that when you normalize the car signal with RxY, basically the probability is the same regardless of the filling fractions. And then note that including nuclear one, which is kind of spin-polarized edge states, right? So the first thing that we can argue that is how come that if you have the spin-polarized edge state, that you can create this Cooper pair into the diamond nitride, which is known to the S-wave superconductor. So this requires at least that spin cannot be a good quantum numbers into the system. And if you just think about the niobium, which actually is a reasonably heavy elements, there's a strong spin-orbit coupling, which will make that the inside of niobium nitride spin is no longer the good quantum numbers, and we have to always kind of tie it with orbital degree of freedom. In that regard, even if that this you have the quantum Hall state with the same spin, let's say nuclear one, right? Due to this spin-orbit coupling, that you can still kind of make the cross-Andreev process. Now, the theorists actually come up with the kind of model of those kind of situation of Bogoliubov-Desjong solve the Bogoliubov-Desjong equations, including the spin-orbit coupling in the superconductors, and see that that describe that the kind of pairing through the pairing of the nuclear one quantum states throughout this superconductor. In that way, open up this the edges, open up this the topologically protected gap in the system. Now, if you just kind of repeat that with this next the edge state, say nuclear two, then there I just add up the another the pair another pair of the counter propagating the edge states, right? Basically, you just go through the same process. Now, the pairing is happening between this newly added state. Of course, now their interaction becomes weaker because they are a little bit farther away. So they open up the gap, but it's probably smaller gap that compared with the nuclear one gap, which is close by, but nevertheless, that topologically protected gap opens up. As long as that gap that opens up is sizable compared with the temperatures and the bias voltage we are just kind of working on, still that those kind of topological protection is happening. And adding up is basically the additional state is basically adding up the copies of this nuclear one states, right? And that can explain that basically P car should be just equal, regardless of any filling fraction in the system.
So the independence of filling occurs only at integer filling. If I consider fractional filling, previously showed it will change.
That's right. That's right.
Oh,
so you see that that's why that if you go to the fractions, right, while the integer equal 2 and 3 is basically similar, right, and that even other values are all the same. The fraction is kind of different, especially the fractional quantum state where they do not have the particle Horn conjugate type of the accompanied integer quantum states. The P car value, the probability is very different. It's actually even stronger than integer values.
Okay, thank you. More questions?
So you had two scenarios for this tunneling effect, whether you have this part. So I first thought that this lower part is impossible since within this okay, so having fractional charge requires the ground state degeneracy and many body effects, whereas in that superconductor, you don't have this ground state degeneracy. how is it possible to have this fractional charge traveling?
Right. I think that's a very good point. But I should kind of mention that I'm not claiming that we are making the Cooper pair of the using the fractional charges. Basically, the Andreev bound states that create this that in this way that you can just basically directly couple that fractional charges on one side and fractional charges on the other side, right? So that doesn't necessarily mean that I'm making the Cooper pair of these fractional charges. Right.
Are you saying that this charge is still existing at the edge or maybe outside of the superconductor?
So I think that the view here is now that there is a fractional, the quantum edge states running down here, right? And I want kind of make this the coupling of this fractional quantum the charge states, right? So using this the superconducting the order parameters, superconducting orders. Therefore, that doesn't necessarily creating the fractional charges inside of the superconductor, right? I think that's kind of what my theory colleagues kind of explained. Then, right? But it is clear that I'm not claiming that I can create this the Cooper pairs out of the fractional charges into the system. So that's kind of the careful distinctions that I'm making this Andreev pairs of the fractional charges at the edge states running side of this superconductor.
Okay, thank you very much.
Yeah.
The last question.
Thank you very much for the great presentation. I have a short question about the geometry of this drain source. If I understand correctly, you mentioned about this the width of this drain W, which should be smaller than the superconducting coherence length. That's right. I wonder about some condition of the length of this drain, whether there is the length scale is important in your experiment, especially for the possible localization at the end of this drain.
That's right. Yes. Okay. So that's also a kind of very important point indeed. Yes, this the length scale is also important because that if I just kind of use the Majorana type of these arguments, basically this distance between these two isolated zero mode is important because that the gap opens up there is proportional, inversely proportional to this length scale. So if this length scale is too short, basically the two zero modes start to impact each other, and you just kind of close down this topologically protected gap. Therefore, that the length scale is kind of important. We don't have the really systematic studies, but it's clear that that about half micron size and micron size of this superconductor length, we see that about kind of equal strengths of the car process is happening. So from there, indirectly, we know that about half micron or longer, basically it's enough the length scale. But at the same time, if you make the really short the superconducting contact, it's clear that we do not see the car process, the strong negative signal. So at least we have the few points that we know that length is indeed a matter. And then the lower bound of the length that we created on the system is at about half micron size.
Thank you very much.
Thanks.
Okay. Now, yeah. Thank you very much, Professor Philip Kim. Yeah, let's move on. Thank you.
Thank you.